Okay, this is chapter 18, which is adaptive immunity or acquired immunity. This is going to deal with the antibody response to a pathogen. So we've already talked about innate immunity, where we have defense against any pathogen. The adaptive immunity is going to be specific pathogen. This usually means that you're going to be looking at antibodies being generated. Antibodies bind to antigen. Antigens cause antibodies to be made. So B cells are made in the bone marrow. T cells are differentiated in the thymus. T cells stimulate B cells to make antibodies. So an antibody binds to an antigen, and the specific region of the antigen that the antibody binds to is called an epitope. And that epitope is a specific molecular shape that that antibody can bind to. Antibodies have a variable region which can change what type of shape they bind to. This is why antibodies are specific for a specific antigen or an epitope of an antigen. And then they have a constant region down here that doesn't change. So there are 5 classes of immunoglobulins, and we're going to talk about them now. IgG, 80% of the serum antibodies, large amount of antibodies. So when it binds to the variable region, binds to the antigen, that is going to allow for the attachment of the antibody to that pathogen. IgG, it's a free-floating antibody. When it's bound to a pathogen, it can also bind complement. That binding to the complement is the classical way to upregulate the complement system. This one can cross the blood placental barrier and the blood vessels. It helps to enhance phagocytosis, and it is good at neutralizing toxins and viruses, protects the fetus. The half-life is 23 days, so it's a pretty long-lasting antibody. IgM, these are larger, so they don't squeeze through blood vessels, so they stay in the blood. They are only 5 to 10% of the blood serum antibodies, so IgG is much higher than IgM. IgM can fix complement as well, and they are in the blood, in the lymph, and they don't come out of the blood because they're so large. However, they are very rarely on B cells. They help agglutinate microbes because if you have a bunch of microbes bound to all these different IgMs, that helps bring those together and makes it easier for identification of the pathogens because they're all in one spot. These have a much shorter half-life, by the way. IgA, these are the most abundant antibody. But it's only 10 to 15% of serum, but however, it is on mucosal membranes, so it provides protection. So all throughout your mucosal membranes, you have IgAs attached, and that is so they can bind pathogens that enter into the mucosal membranes. IgD, the key to remember for IgD, they are attached to the B plasma cell membranes, or B cell membranes as well. So IgE, allergic reaction, or parasitic worms. So how do we activate a B cell? Well, there can be 2 ways. There's a T cell dependent activation, and there's a T cell independent. T cell independent is shown here, where multiple IgDs, which are on the surface of the plasma membrane for a B cell, bind through their variable region to the antigen. So these antibodies are binding to the antigen. That's going to stimulate that B cell to make antibodies. However, it's only that B cell that makes antibodies, and there is no memory cells made, so it's a very weak response. Now, T cell dependent B cell activation involves an APC, which is an antigen presenting cell, or a professional presenter. That's going to be a dendrite, a neutrophil, a macrophage, or even a B cell itself. So what happens is that, for instance, a neutrophil, it finds pathogen, binds through its toll-like receptor to that PAMP, and it's going to do receptor-mediated endocytosis, which we call phagocytosing, processing, and presenting. So now we are receptor-mediated endocytosing, and now we are presenting. So that now presents. So this is the phagosome fusing with the lysosome. That's going to chop it up, and it's going to present a piece of that pathogen. So MHC1, major histocompatibility class 1, are on all cells that have a nucleus. MHC2 are only on APCs. So what we have is a T cell binds through its T cell receptor, and that T cell receptor is specific for that piece of antigen that is being presented on the APC. In this case, it's our neutrophil. When these two bind through MHC class II to the T cell receptor, that's going to cause the APC to release interleukins, which stimulates clonal expansion of that particular T cell. So here you can see that the correct shaped T cell receptor can bind to that antigen. That causes mitosis to happen, and we're going to make memory cells, and we're going to make a lot of those T cells. Now, at the same time, you're going to have a B cell that can bind through its IgD that binds to that antigen. So that B cell must have the correct variable region of IgD to bind to that pathogen. Once it does, it's going to do PPP, phagocytosine processing and presenting. Through its MHC class II, it's going to present that antigen.